Hello, everyone, and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
I am Corinne Caputo, writer, comedian, friend of the universe.
Yeah, you are. Mm-hmm. And I am Dr. Moiya McTier, astrophysicist, folklorist, and also bud to the universe.
Hell yeah, bud. Top 8. Did you ever do MySpace?
So many people have asked me recently. I don't know why this is coming up so often in my life, but no, I never had MySpace.
I think that's
and
I
never had like AIM. Mm-hmm. I got Facebook pretty late. Like I kind of grew up under a rock.
I think that's good because I think it broke me.
Oh no.
There's just like so many social things you don't know how to emotionally do when you're that young on like MySpace, and like our parents' generation never had social media either. So you're like, oh my God, I'm not on her top 8. This is the end of the world.
That did seem like it came with a lot of pressure and stress.
Yeah. Mm-hmm.
Yeah. And our parents couldn't help us with it.
No, they're like, what are you talking about?
Yeah. Oh, well, we don't have to be in a stressful internet chat room.
Not today.
Where are we, Corinne?
Okay, I wanted to be somewhere that was brightly lit, surrounded by happy people usually, because our topic today could feel a little dark and scary before Moiya explains it. So we are on a bench in Central Park, the iconic park of New York. Mm-hmm. I love this park.
Yeah, I love this park too. I try to go to Central Park as often as I can. Like ideally I would go every day, but that doesn't always happen. I love that the benches in the park are dedicated to people.
I know.
So sometimes I'll choose the bench that I want to sit on based on my mood.
Oh, I like that.
And I don't know these people. I know nothing about them but their name and like maybe a tiny bit of information, but I just go off the vibes that their name gives me.
Yes.
And then I'll choose what bench to sit on.
I love when there's like something that reveals the personality of the person. Mm-hmm. Like instead of it being like in loving memory of, it'll just be like with many laughs thanks to, just like something different.
Mm-hmm. Yeah, just a little variety. It is, after all, the spice of life.
It is.
That's what I hear.
The funniest, I went to this park once after an eye doctor appointment, and I didn't bring my contacts with me, or I didn't bring my glasses with me. I usually wear contacts, and they had to dilate my eyes. So I had to leave the appointment with, I can't see far away normally, and now I couldn't see close up either.
Oh, no.
And I was like, I don't know. I got lost in the park because I couldn't read the street signs, and I couldn't read the map on my phone.
That's a nightmare.
It was actually extremely funny. And it was like, it was like the middle of the day. Like, I knew it would wear off soon, but it was definitely like, this is a silly thing I've done.
I mean, I've gotten lost in Central Park without eye stuff.
Without dilated pupils.
Yeah, because it's, the paths, they're curvy. And
they really are.
I don't know if I've said this on the pod before, but I am extremely navigationally challenged.
Yep. So am I. Mm-hmm. I never know where I am almost.
Nope. That's why I have to live in New York City with a grid.
Yes, you need the grid.
I do. Otherwise, I would never know where I am. But it is, I love that you asked me to come record this episode here today, Corinne. You're right. It is going to be nice to be in a shiny place, a bright, shiny place full of happy people. Shout out to the REM song, maybe. Because today we are talking about black holes.
Ooh.
Which is a big topic in astronomy. I know that a lot of people have questions, a lot of questions about black holes. I know that they can give you a sense of dread, maybe, if you feel that reaction to the universe.
Oh, yeah.
And things in it. But I am here to demystify black holes for you. And hopefully by the end of this episode, they'll feel just a little bit more familiar and a little bit less scary. Because I'm here to tell you, I will tell you right at the top of this episode, a black hole will not hurt you. There aren't any nearby, and even if the sun were to spontaneously turn into a black hole, which wouldn't happen, there's no physical process that would make that happen. We'd be fucked. but not for the reason you think. We would not then immediately...
Because
we need a sun. We need the warmth and the light from the sun.
Yeah.
But our orbit wouldn't change at all. Black holes, contrary to popular belief, they do not suck things in like a vacuum cleaner.
This is wild to hear.
Really? Okay, good. I'm glad we're starting with the misconceptions up top.
I think of them as a vacuum, as like a literal, not a literal vacuum, like a household vacuum.
Mm-hmm. A lot of people do.
I hope this episode serves as a rebrand for black holes.
Yeah, that'd be nice. Especially since I gave black holes such a bad reputation in my book. But yeah, black holes are not like household vacuum cleaners. They do not just suck things in. Black holes are just like big pits. They're big gravity pits, and things can fall in, but they are not getting sucked in.
Okay.
Yeah.
Good.
Yeah. So let's get that out of the way right off the bat. A black hole is, by definition, an object so dense with such strong gravity that their escape velocity is greater than the speed of light. And one of the fundamental truths of the universe is that nothing moves faster than the speed of light. At least that's how we understand the universe right now. If you are interested in equations and you would like to calculate the escape velocity of any object with mass and therefore gravity, here is that equation. The escape velocity is the square root of 2 times the gravitational constant, which we talked about in the fundamental forces episode, times the mass of the object that you're trying to escape, all over the radius of that object that you're trying to escape.
Okay.
So it's...
I'll never do that equation.
That's fine. That's totally fine. But it is the square root of 2gm over r. You can calculate the escape velocity for anything with mass, and a black hole, canonically, has the escape velocity c, which is the speed of light.
Whoa.
We can get into the anatomy of a black hole to start. I think that might be... like if we can help people picture... a black hole's body, maybe that will help a little bit. So in the center, you have the black hole itself, which is the gravity pit, which is the dark thing that we call black because it's so dense, light cannot escape it. So we don't see the black hole because it's like we're not getting any photons from the black hole itself. The black hole is the, sometimes people will call it the singularity.
Yes, I've heard that.
Outside of the realm of artificial intelligence, a singularity is a point of infinite density. It's really, really dense. That's the concept you need to grasp for this episode. Immediately surrounding the black hole, like the edge of the black hole, is called the event horizon. It is not a physical barrier or boundary. It's just this like mathematically constructed horizon for the black hole. The size of the black hole, or like the location of that event horizon, is often calculated using something called the Schwarzschild radius. Have you heard of this?
No.
That's cool.
Schwarzschild.
Yeah, it's German, I think.
Sure.
Yeah. So the Schwarzschild radius, to calculate it, you can just rearrange that velocity, the escape velocity equation, to solve for r. Because the Schwarzschild radius is the radius where the escape velocity for an object with a given mass is the speed of light. So if you set the velocity in the escape velocity equation to the speed of light and you resolve it for r, then you would get the Schwarzschild radius.
Okay.
Around the black hole, you often see what we call an accretion disk. You can see this around newly formed stars too. The accretion disk around a star is where the planets form, but the accretion disk around a black hole doesn't have exciting stuff like that happening. Instead, it is the disk of stuff that is actively falling into the black hole. Notice I did not say it's the stuff getting sucked into the black hole.
Okay.
Because that's not what black holes do.
I did notice.
It's just falling, and it takes a long time for material to fall into a black hole. But because black holes are quite dense and quite massive, they're all at least as massive as our sun, then the material in the accretion disk has to move really fast. Because the closer you are to a massive object, the faster you have to move, or else you'll fall in. And they are falling in, but they're not immediately.
Yeah.
So they move so fast, and the particles in the accretion disk rub together a lot, generating heat. So you can see temperatures of millions of degrees in these accretion disks. They get so hot that they start to glow. So when we see a black hole, usually we're just seeing the accretion disk around it.
Sure. Okay, that makes sense.
So that accretion disk will can glow really strongly in X-rays, but we can also study black holes in the radio wavelengths or in infrared wavelengths. Or in optical. Like, we can see them in a lot of different wavelengths, but because it's so hot, they're really giving off a lot of X-rays. And then you wouldn't see this in all black holes, but the really powerful ones have these jets of glowing material that shoot out from their poles. So the spoiler alert, black holes spin just like planets do.
Whoa.
Pretty much everything in space is spinning. Planets do it, moons do it, stars, black holes, galaxies, everything is spinning. Because angular momentum has to be conserved in the galaxy. So if you have multiple objects coming together on some sort of path or trajectory, they will hit, and like their momentum, their trajectory will be combined, and they'll spin. It's like if you're ice skating, and your friend comes and hits you from one direction. Moving. Yeah, like if they come to you from your right, you will then, they'll hit you and their momentum will be added to your system and you'll spin in that direction, in that same direction. So everything in space is doing that too. I talk about the spinning because that means that black holes have poles. They have like a north and south pole, just like the Earth does, because that's based on its axis of rotation. And these jets will spit out of the north and south poles, and they move at like 99% the speed of light. So we call them relativistic jets. Relativistic is the word we use to describe anything that goes at like any significant fraction of the speed of light. You know, if something goes like 5% the speed of light, we're going to call it relativistic.
Okay.
These relativistic jets, for a long time, were a mystery, and we're still actively trying to learn more about them. But now we're pretty sure that they are formed because of magnetic field lines, like so much stuff in space. So magnetic field lines happen whenever there is motion of charged particles. We've talked about this a lot on the pod before. As the black hole rotates, those charged particles and the magnetic field lines that they produce, they get concentrated towards the poles of the black hole, and they form these long columns of magnetic field lines that the charged particles can shoot through. So the jets we're seeing are the charged particles from the accretion disk getting trapped in the magnetic field lines at the poles and then shooting away because of all the energy in them.
Okay, I'm looking at some illustrations of this on Google Images, and it does seem very powerful. Like there is a kind of like a climactic event that would happen in a movie where suddenly there's this like explosion is what it kind of looks like.
Except it's not an explosion because it's not instantaneous. Right. These jets stay. And it's just like a constant feature of these really powerful black holes.
That's really cool. I feel like you don't see something with lines like this unless it is explosive. But that's certainly me and my limited like sci-fi inner like download. So to me,
it looks
I'm
like a laser.
Yeah, exactly.
No, but these relativistic jets are only in the most powerful black holes that we call active galactic nuclei, or AGN for short.
Active galactic.
Active galactic nuclei are black holes that are so massive and so powerful that they are accreting a lot of material, which gives them these powerful relativistic jets. It also gives black holes like these winds that shoot off of it, kind of like the solar wind that comes off of our sun and other stars. But there's, you might have heard the terms quasar and blazar.
Quasar, yes. Blazar sounds like a weird twin brother of this.
Yes. Yeah, it pretty much is. So a quasar is one of these active galactic nuclei that has the relativistic jets, and we call it a quasar. It comes from quasi-stellar object, which is what we called it before we knew what it was, because all we would see was this bright point of light. in the distance, and we knew it wasn't a star because it was too far away to be a star, but we didn't know what it was because we couldn't see the black hole in the center. So we were like, that's a really bright object, we're going to call it a quasar, and then we realized it was black holes with jets. But those jets can be pointed in like any direction, right? So sometimes the pole of the black hole that the jets come out of are pointed at the Earth, which means we see like the full brightness of the relativistic jet. And when we do see the full brightness, we call it a blazar, which is a blazing quasar.
Oh, that's cute.
So they're the same thing. It's just a matter of angles.
I like that. That's a naming convention that fully makes sense to me.
Yeah, it's nice. If you would like to learn more about blazars, I would recommend looking up Dr. Jedida Eisler's TED Talk. Jedida is one of my favorite humans on the planet, and she is a TED Fellow. She gave a talk about blazars, which is what she studies, and she gave a talk about like getting minoritized and marginalized people more into STEM. She's amazing.
I
Highly
love
recommend
that.
looking up her work.
Oh, I can't wait.
So that's the anatomy of a black hole, which is one way that you could describe black holes in general. But if you wanted to describe a specific black hole, according to Einstein and other scientists who really care about gravity in black holes, a single black hole can be described by 3 different numbers: its spin, its charge, and its mass.
Okay.
So I'll go into each of those. I'm going to start with spin because spin is the reason that black holes have relativistic jets in the first place. So I thought that it would be a nice like continuation of what we were just talking about. So the spin of a black hole is all of the combined angular momentum present in the system. So all of the stars, all of the gas and dust that fell into the black hole, even the angular momentum of depending on how the black hole formed. If it formed from a star, we have to include the angular momentum that star had when it was spinning during its like normal life phases. So you add up all of the angular momentum in the system and you get the black hole's spin. But because there's a lot going into the system, black holes spin near the speed of light.
Whoa.
So this is like you find black holes are really extreme environments.
Yeah.
They're the densest things. They're like the fastest things. You know, they're spinning near the speed of light. They have these jets that shoot out near the speed of light. So it's a really energetic system.
Yeah.
But they spin so quickly because they're so small. Picture again a figure skater and they're spinning and they have their arms out. If they pull their arms in, they'll start to spin more quickly because of the conservation of angular momentum. They now have a smaller radius, but they still have the same amount of kinetic energy, so they have to move faster to account for that. And by studying the brightness and the spectrum, we've talked about spectra before, if you study the brightness and the spectrum of a black hole's accretion disk, you can measure the black hole spin. Because you can't just look at a black hole and see how fast it's spinning, because you cannot actually see the black hole itself. You can just see the stuff around it. It's a weird consequence of general relativity. It's kind of counterintuitive, and there are a lot of counterintuitive things in the science of black holes. But the faster a black hole spins, the closer its accretion disk can get to the event horizon. Like physically, the two items can be closer if the black hole spins faster.
Okay. That makes sense.
Does it?
To me, that's like it's spinning faster because I'm picturing this figure skater bringing their arms in, and I'm picturing this getting like closer to them.
Oh, okay. I like great.
Scientifically, who knows? But for my head, it works.
That's what matters. That's how I remember a lot of stuff in astronomy. I just come up, and science in general, I come up with these little like stories or these little mnemonic devices, even if it's not scientifically based, as long as it gets me to the right answer. It works.
Who cares?
The fastest spinning black hole that we've found to date is Cygnus X1, which is coincidentally the first black hole that we ever found.
Whoa. Well, did we find it because it was the fast? Like, was it more obvious because of that? No. Oh, no. Interesting.
This is a distant, a black hole in a distant galaxy. It was discovered in 1964. Like the source was discovered in 1964, but we didn't know what it was until much later. So Cygnus X1, discovered in 1964, About 10 years later, Stephen Hawking and Kip Thorne, who you might remember was the science advisor to the movie Interstellar, they made a bet. They placed a bet on whether or not Cygnus X1 was actually a black hole. And they bet, like, magazine subscriptions.
That's so funny.
So, like, if Stephen Hawking won, he got some magazine subscription. I don't remember what his was because he lost. He bet that it wasn't a black hole. Stephen Hawking believed in black holes, but he didn't believe that humans could detect them.
Okay.
So he was like, nah, Cygnus X1, that's not a black hole. We wouldn't be able to see that. But Kip Thorne was like, oh, no, it's definitely a black hole. He won the bet, and in 1990, when it was confirmed to be a black hole, Thorne won a year-long subscription to Penthouse magazine.
Oh my God. Of course. Well, I'm thinking of it like a gift where it's like, well, this is something I'd never buy myself, but like it's definitely a treat I want.
for betting on the first black hole ever discovered.
Yeah, that's so funny.
You know, and then it was only recently, like in the last couple of years, that we measured Cygnus X1's spin and realized that it's like the fastest one we found.
Wow.
But also, they're all spinning at near the speed of light anyway, so
when you get to be that fast, sure.
So that's spin. The next number that you use to describe a black hole is its charge, its electric charge. Mm-hmm. And usually scientists assume, or they approximate, that a black hole has a neutral charge because positive charged particles are just as likely to fall into the black hole as negatively charged particles. Okay. So you would expect it to balance out. But this is an idealized simplification of reality, which is how a lot of astronomers, when we're doing our models and our simulations, we have to simplify things and we have to imagine ideal scenarios because there's so much that goes into stuff in space that it would take too much time and computing power to accurately account for all of the different factors. So we simplify it a little bit.
Sure.
But there is this one study that I found from 2019 that showed maybe it's not the best idea to make this assumption, especially when you're trying to figure out how black holes affect their immediate surroundings. Because in this study, they found that a charged particle passing by a black hole that does have some electric charge would experience 16 times more electromagnetic force from the black hole than they would its gravity. And black holes have extreme gravity.
Yeah.
A black hole's gravity is so extreme that it rips things apart. It's called spaghettification, which is really fun.
Yes, I've heard of that, and that's why I'm afraid of them.
Yes, but you have to be really close. You have to be like in the accretion disk, essentially, to be spaghettified by a black hole. Mm-hmm. But they're saying that charge is really important here. So let's pay more attention to that number when we're doing our models going forward. If you have like the time and energy to do that. And then the third number is a black hole's mass. This is the most important number because it determines the gravitational effect that the black hole will have on stuff around it. And a black hole's mass can range from a few times the mass of our sun to like many billions solar masses.
That is a lot.
They're so heavy.
Because I'm thinking of how our sun is so big. It's like almost incomprehensible to me to understand how big it is. So I can't imagine a billion of them.
Yeah, these black holes they're chunky.
They're chunky.
They're big boys. SZA would be quite pleased with a black hole. So that's spin, charge, and mass. But I did want to talk about a fourth number related to black holes that you don't need to use if you're like trying to capture the essence of a black hole scientifically, but it is useful, I think, and that is the accretion rate of a black hole. So how quickly does the black hole devour or accrete more material? These accretion rates can be approximated with the Eddington accretion limit. Sir Arthur Eddington was one of Einstein's contemporaries who did a lot of work figuring out how big can a star be, or like how bright can a star be based on its size, and also with accretion, like how there's this limit in accretion where if you are absorbing enough material, you're going to radiate away energy. And at some point, like as you're radiating away stuff, there's a point where it will overcome gravity. So that's the Eddington accretion limit. There's this other way that you can calculate accretion rate with a different type of accretion called Bondi accretion, where you imagine this spherical system that is gathering material in a spherically symmetric way. I did that math. I did those classes, but we don't have to get into the details of that. The black hole at the center of our Milky Way galaxy has an accretion rate of about 5 billionths. That's not 5 billion. That's like that's 5 divided by a billion. 5 billionths of a solar mass per year.
So not much.
It's really small.
Yeah.
No, it's not much. And I think that that's why I wanted to include the accretion rate here, because people think of black holes as these, like, sucking,
it's just gobbling,
hungry
gobbling,
monsters.
gobbling.
Yeah. But they actually aren't. Our black hole is kind of average.
Wow.
In that. So some have higher accretion rates, many have lower accretion rates, but all in all, accretion rates aren't that high. Black holes are not guzzlers of stuff.
They're not the hungry hippos of the universe.
No, they're not.
Hi, it's Corinne, here to give a shout out to our incredible patrons who are supporting this podcast. It means so much to me and to Moiya and to everyone who helps make this show. So thank you, as always, to our sun-like stars, Sharn Llewellyn, Finn, Ian Williams, and Megan Moon. And thanks to our latest pre-main sequence stars, Jessica, Elise, and Eric. You too can support us, hear your name on this pod, and make it to our patron star chart, all by supporting us on Patreon. Find the star chart, Patreon info, and more at our website, palebluepod.com, or go straight to the source at patreon.com/palebluepod.
Hey, it's Moiya here to tell you that Multitude, which is the podcast collective that Pale Blue Pod is a member of, finally has its own merch. You can grab a Multitude logo tee or crewneck sweatshirt now at multitude.productions/merch or at the link in this episode's description. So right now it's just the t-shirt and the crewneck sweatshirt, but more merch is on the way, so you can stay tuned for updates. And as a reminder, all multi-crew members at the $10 tier and above will always get 10% off of all Multitude logo merch. Please order the merch. I'm really excited to get my sweatshirt, and once I do, I will post that on socials. But if you order, then when you get it, you should also post on socials and tag Multitude and let us know. Are you Team T or Team Crewneck? That way we can settle this debate once and for all. So go to multitude.productions/merch or to the link in this episode description to get yourself some Multitude swag. The fact that you're listening to this show tells me a couple things about you, and I can recognize those patterns because I am a scientist and an analytical thinking genius. But here are the things I know. 1, you're listening to an astronomy podcast, so you clearly like to learn. But 2, you're listening to specifically this astronomy podcast, which means you like to learn in fun and friendly and interesting ways. So please let me tell you about Brilliant.org, which is the best way to learn math and science interactively online. Brilliant has thousands of lessons in math, science, and data analysis, and they're adding new ones every single month. Brilliant doesn't just teach you facts and formulas. They actually help you develop your intuition for these subjects through interactive gameplay. So their science courses can help you get a deeper understanding of things we talk about a lot on here, like planetary orbits with their classical mechanics lessons, or particle physics with their quantum objects course. Whatever you learn on Brilliant, you'll have a fun time doing it, and it will strengthen your general analytical thinking skills, even outside of the specific topics that you're learning about in your lessons. So you, as a Pale Blue Pod listener, can get a 30-day free trial by going to brilliant.org/palebluepod. And the first 200 people who sign up using our code will get 20% off their annual subscription. Again, that's brilliant.org/palebluepod for a 30-day free trial. And then if you are early enough, if you're an early adopter, you will get 20% off your annual subscription. We're all about getting cozy here at Pale Blue Pod, and I always feel the comfiest when I can sit back and relax with maybe a good book, but like definitely a really good smelling candle. So I'd like to recommend the Queer Candle Company. They're a small batch soy wax candle company. They hand pour their candles with love. They're also queer and trans owned. The candles are topped with a variety of botanicals, including pressed flowers, dried herbs, and zested aromatics. And friends, I got one of the dark plum candles from the Queer Candle Company, and the only way I can describe it, now I don't believe in heaven, but if I did, I am pretty sure that this candle smells like dark, sexy heaven. You know, not hell, because there's not torture, there's not fire and brimstone, but it smells so good, and I want to bathe in this scent. The Queer Candle Company donates 10% of their monthly profits to the Sylvia Rivera Law Project, and they also sell DIY refill kits online so that any of their candles are endlessly refillable. You can use the code PALEBLUE at checkout to get 10% off your first order on their website, queercandleco.com. So go to queercandleco.com, type in pale blue for 10% off, or check out their Instagram and TikTok at queercandleco. Highly recommend the dark plum. Like I said, dark, sexy heaven. What's not to love? So there are these three different numbers, mass, charge, and spin. And when scientists try to model or study black holes, they're using different assumptions and different simplifications each time. So if you have a black hole and you're assuming that it's just massive and it doesn't spin and it doesn't have any electrical charge, then you're talking about this hypothetical Schwarzschild black hole. Mm-hmm. If you are talking about a black hole that has mass and it spins, but it has no electrical charge, then you're talking about a Kerr black hole, Kerr, named after the New Zealand mathematician. We don't see a lot of scientists from New Zealand in astronomy. From the Kiwi mathematician Roy Kerr, who theorized for the first time a spinning black hole back in 1963.
Is this any relation to Miranda Kerr, the model who was once married to Orlando Bloom?
I hope so. I really hope so. Is she from New Zealand?
I think she is.
Oh, maybe.
She's an Australian model and businesswoman. So not New Zealand,
that's quite
but
close.
Pretty
he
close.
Might have moved.
Yeah.
Okay, well, we'll look this up later.
Science and pop culture overlap again.
Together. It's a beautiful marriage. If you have a black hole that has mass and charge but no spin, then you're talking about a Reissner-Nordstrom black hole. And I really doubt that it's like Nordstrom from the store, but maybe.
I love malls. I'll say it on the podcast malls. Again. I love malls.
Things I know about Corinne now that I didn't before we started making this podcast. She has a twin, and she loves malls.
I really do.
If you are talking about like an actually realistic black hole that has mass and electrical charge and spin, then you're talking about a Kerr-Newman black hole. So these are the types of models that we would use in our simulations or in our math to study different black holes, based on what computing power we have available and what question we're trying to answer. So those are different types of black holes according to like their numbers. A lot of people also classify black holes by their mass.
Yes.
So there are let's say three. There are, broadly speaking, three types of black holes if you're grouping them by their mass. And so I'll go through each of them now and say how we think they form.
Okay.
The first and the most common is a stellar mass black hole. Okay. These are the lowest mass black holes that can be from like a few times the mass of the sun up to about 50 times the mass of the sun. And these black holes form from collapsed massive stars. So we talked about this in our stellar types episode. The O and B type stars will form either a neutron star or a black hole at the end of the star's life. So I guess it's just O stars. O stars will form a black hole at the end of their star's life. But stars, as they're getting to that phase, they'll lose about 60% of their mass before they collapse back into whatever remains.
Okay.
So because these stars have starting masses of like 100-ish solar masses, up to like anywhere from like 30 to 100 solar masses, then the resulting black hole is going to be like a few to like 30 or 40 times the mass of the sun. So there you go. How many of these stellar mass black holes do you think there are in our galaxy?
Oh, this is such a question, because to me, black holes could be almost nowhere or everywhere. But I think we've talked about this, and there's not like just a handful of them, right? There's a ton?
There's a ton.
Okay. Then I have no idea, because I was about to say one.
There's the one famous one that we have in our galaxy. That is not a stellar mass black hole, though.
Okay.
We'll talk about that in a second. So there should be at least 10 million stellar mass black holes in our galaxy alone.
I'm not going to fall in.
You're not going to fall in. No. A black hole cannot hurt you.
It won't eat
where
me.
You are.
It
Corinne.
won't eat me.
No. So about 1 out of 1,000 stars is massive enough to become a black hole. And there are like 100 billion stars in the Milky Way galaxy. So do that math. It's like 10 to 100 million.
Wow.
But in our galaxy alone, I did see a paper that will be in the research notes for our patrons that estimates the number of stellar mass black holes in the entire universe. And it's a lot. It's a really big number. They estimated that stellar mass black holes should account for about 1% of the regular matter, the baryonic matter in the universe.
Whoa, that's a lot.
It's a lot because they're so big, they're so dense. So those are stellar mass black holes. We know how they form. We are pretty confident that we understand stellar mass black holes, even though we can't really see them. Because they are not big and massive enough to have accretion disks around them or relativistic jets. They're not powerful enough.
Okay.
So we can't really see them. They're just floating through space. But we can, and we do, see a lot of supermassive black holes.
Now, this is a name that I know.
There are songs written about them. There are movies about supermassive black holes. I'm pretty sure that most people have heard that there's a supermassive black hole at the center of our galaxy.
Yes.
And more than that, pretty much every galaxy we have studied has a supermassive black hole at its center, which leads us to the question, did the black hole form first or did the galaxy form first?
Whoa.
And we're not really sure. So we know a lot less about supermassive black holes than we do about stellar mass black holes, or at least we know less about their origin.
Sure.
But their formation is largely a mystery, especially when we see galaxies from very early in the universe. I'm talking less than 1 billion years after the Big Bang, with massive black holes in their center. That's confusing. How did they grow so fast?
Yeah.
But some studies suggest that supermassive black holes form through collisions. So you have smaller, maybe stellar mass black holes that collide and build up size and mass over time. Also, galaxies collide. And since we know galaxies have the supermassive black holes at their center, when the galaxies collide over time, so do their black holes. But that still leaves the question, how did those galaxies get the supermassive black holes to begin with? So one hypothesis is that the seeds of these really massive black holes, like the progenitors, would have been something called a primordial black hole.
Okay.
From very early in the universe, which wouldn't have been constrained in terms of mass in the same way that black holes are today. So a primordial black hole, one way that it could have formed early in the universe when, like, stars were just starting to form and galaxies were just starting to coalesce together, and there was a lot more, like, regular hydrogen in the universe that hadn't been converted into heavier elements. So all the way back then, if you imagine a giant cloud of gas that is close enough to another galaxy emitting ultraviolet radiation, then that gas cloud would stay hot because of the radiation from the nearby galaxy. Usually, gas clouds will cool down and they'll condense and they'll cool down more, and the cooling creates these little clumps of gas within the cloud, and those clumps become stars.
Okay.
But if the gas cloud isn't allowed to cool down, if it stays hot, it will still contract, it just won't get clumpy. So instead of forming a bunch of stars, it would form a big black hole with a mass of like hundreds of solar masses. And over time, if you have a lot of those big black holes, they could combine together to make a supermassive one.
It feels like a cooking technique of like, just don't cool it. And then you'll see that.
I don't know why, but the image of making a poached egg, like the image of poaching an egg just came to mind.
Sure, yeah.
Because it's like, you know, you put the egg in, it's a cloudy thing.
Yeah.
And if you have the vinegar, it's going to clump better. And if you don't have the vinegar, it will clump worse or something.
This is evidence that we're living inside a kitchen simulation. This is
evidence. You're right. Irrefutable evidence. This weird, loose analogy that I just made is irrefutable evidence that we're living.
I solved it. Me, conspiracy theorist now.
It's specifically a kitchen-based simulation.
Yes, I'm starving.
So that is one way that you could form supermassive black holes. The biggest, the most massive black hole we have found to date is called TON, T-O-N, 618, and it is a quasar, so it's an active galactic nucleus. It has those jets, but they're not pointed at us. It is a quasar with a mass of 66 billion suns.
No, that's so many.
It's a big boy.
Really?
It's a really big black hole. And we are still actively trying to figure out how they get that big, because the whole like primordial black hole thing is just a hypothesis.
Right.
It has not been proven. So I've talked about stellar mass black holes and supermassive black holes. There is this gap in the middle from 50 solar masses to 50,000 solar masses. We're like, where are all of the black holes?
Yeah.
There? We call those intermediate mass black holes.
Okay.
And at first, astronomers thought, well, there must be intermediate mass black holes because there are stellar mass black holes and they should build up over time to make the supermassive black holes. But there's a progression there.
Yeah.
But then we didn't see any for a really long time. So astronomers started to think maybe there aren't any intermediate black holes. Like maybe the mechanisms, the processes that create black holes just don't make black holes of that size, which really... it threw a wrench in the whole idea of supermassive black holes being created through collisions. But now we have found a couple of intermediate mass black holes, so we know they exist, but they seem to be pretty rare. Although, that could also just be an observational bias, like maybe it's just really hard to see them because they probably don't have bright accretion disks and relativistic jets.
Sure.
So... what I'm saying in this part of the episode is that where black holes come from is kind of a mystery for some of them, for the biggest ones. Any questions so far about black holes?
This is definitely making them make more sense to me. I do have the kind of sci-fi blockbuster vision of what a black hole is, which is that it's just sucking things up, and somehow I will be involved personally in that one day.
But now you know that's not true.
And I definitely think of them also as like this, maybe I read a book or something during a vulnerable age, but I think of them as like a who knows what's in there kind of thing. Yeah. Of like, am I going to emerge in a parallel universe? And I have no idea.
We have no idea. The brightest minds in the world have no idea, Corinne.
That's what scares me.
But we do all know. All of the smartest people in the world will agree that we are not in danger from a black hole where we are in the galaxy.
That's a relief. I feel like my parents telling me when I was afraid of the dark at night growing up, they'd be like, you have nothing to be afraid of. And it didn't always soothe me. It's like, I know, but I feel scared.
But like... in that scenario, the dark is there.
That's true.
It's around you. It's immediate, and that is terrifying. But there aren't black holes around.
You're right.
What I'm saying, like,
so true.
I think that everyone should be very comforted by the fact that there is no black hole anywhere near us that could pose a danger.
Mm-hmm. So true. And I love spaghetti, so it wouldn't be the worst to get spaghettified.
Right, to be a food that you love so much.
To finally become what I love.
Mm-hmm. And, the temperatures are hot enough, you'll get cooked.
Yeah, exactly.
And they do kind of look red in the pictures, so that's kind of like sauce.
Red sauce is my favorite.
Come back next week when we talk about other astronomical phenomena and the food that they remind us of.
I did that in one of the Zoom, the many space Zoom classes I did when peak COVID hit. There was one where I just showed kids pictures of comets and then the potatoes that I thought they looked just like, or meteors and asteroids, and then the potatoes that were shaped the same way.
Or are these just the potatoes that you had?
If there's ever
a
Pale Blue Pod live show, I'll present the potatoes. The potatoes.
You mean when there's a Pale Blue?
I'm gonna do a potato presentation.
I'm holding you to that, Corinne.
Yes, you can.
That is locked in my brain box. I'm gonna bring that up. Okay, so we're feeling better about black holes.
Yes, we are.
And the lack of danger that they pose. Good. So we just talked about how black holes form. To me, in the way that I thought it made sense to organize this episode, that then made me think, can black holes die? Because we often talk about stars dying, which is language that I don't love.
Mm-hmm.
I think it's better to talk about stars as just evolving to the next stage of their life. But can black holes die? Do they have a next stage of their life? It turns out, short answer, yeah,
Whoa.
They can die. Mm-hmm. This is counterintuitive. Like I said, a lot of stuff with black holes is going to be counterintuitive. But we say that nothing can escape a black hole because its escape velocity is faster than the speed of light. But that's not entirely true. It just happens very slowly and on extremely small scales.
Okay.
So in the 1970s, Stephen Hawking, the same Stephen Hawking who made several bets, actually, not just the one with Kip Thorne. They're articles about Stephen Hawking and his four
He's a
scientific
gambler,
bets.
yeah.
But only with magazine subscriptions.
Sure.
So Stephen Hawking, who had the same birthday as me, fun, obviously not the same year.
Yeah, I know you're not as old as Stephen Hawking.
Cool. So in the 1970s, Stephen Hawking tried to figure out if black holes have a temperature. We know that the accretion disk gets really hot, but what about the black hole itself?
Yeah.
So he did some thinking, and he did some math, and he sat around in his chair, which is what theoretical physicists do. And he came up with the answer, yeah, they do have a temperature, but just barely. And I'm talking 10 to the minus 10 Kelvin, which is way colder than the average temperature of the universe. So black holes themselves are very cold, but they do have some temperature, which means they are emitting some sort of radiation.
Okay.
In doing this exercise, Hawking realized that black holes slowly radiate their energy away, and that after many years, 10 to the 50 years, a black hole could completely evaporate away.
Wow.
As long as it's not actively accreting material.
Yeah.
Mm-hmm. So this works because around a black hole, these pairs of things called virtual particles can form right at the event horizon. And these virtual particles are usually anti-particle-particle pairings, so a neutrino and an anti-neutrino, or an electron and a positron or something.
Okay. Just the twin, the good twin and the bad twin.
Exactly. Yeah. So around a black hole, spontaneously, these good and evil twin pairs of particles can form, and they would form around the event horizon, straddling the event horizon of the black hole, because it's not a physical boundary.
Sure.
So the thing that's on the inside, the particle on the inside of the event horizon, would get sucked into the black hole, or would fall into the black hole. I'm going to be careful with my language. And then the virtual particle on the other side would get to escape.
Okay.
These particles, and I'm glad that we have already done an episode where we talked about quantum field theory, because I don't have to explain that again. Go listen to the episode on fundamental forces if you want to learn more about how I think of quantum field theory. But these particles, these virtual particles, form from fluctuations in the quantum fields around the black hole, which, and the black hole itself is bending space-time so strongly that these quantum fields can have more energy in one location than they do in another. And there's this extra time weirdness because black holes, their strong gravity can actually dilate time. So it's like these quantum fields at the same time, but also at different times, have different amounts of energy.
Whoa. When we start bringing time into stuff, my brain is immediately checking out. It's just like, I think I'll explode if I learn too much about myself.
Yeah, quantum stuff is weird. And the way that I deal with it is just kind of like shutting off the part of my brain.
The ego. That's
well, not the ego, but shutting off the part of my brain that's like the why kid.
Yeah, sure.
You know, like the kid that's going to ask why over and over and over again until they're satisfied. I have that part of my brain. And it's usually good at helping me learn.
Yeah.
But when it comes to quantum stuff, I have to turn that off and I have to just accept things at face value.
Yes.
So let's just accept at face value that around black holes, time and energy are weird.
Mine is fully ego. It's fully like, oh my God, what if this makes me more insignificant? Like,
oh no.
No, it's like
nothing
it's
can make you less significant.
Corinne, am fine, but the voice in my head that wants to be important is like dying to be important.
If I can't be important, no one can.
Yeah. When we named these characters the other day, mine is Karen. So.
Mine is Carl. Well, Carl, I don't think of Carl as my ego. Maybe he is. I don't know. Carl's just the mean voice.
I think Karen has a lot of goals. She's on a mission.
Well, I do usually admire and respect a woman on a mission, but not right now because fuck Karen.
Fuck Karen.
So these black holes that make time and energy weird can very slowly radiate away their energy. But more massive black holes radiate their energy more slowly. So it takes a massive black hole longer to evaporate due to Hawking radiation. And this Hawking radiation usually isn't like important to think about because it's on such long time scales.
Yeah.
But I think the one place where it's interesting to think about is when you get into discussions about the end of the universe. I'm going to give you and the listeners some space, a moment to come to terms with the fact that we're about to talk about the end of the universe. So take that moment.
I won't be around. I won't be around. I won't be around.
None of us will be. There are a handful of potential scenarios for the end of the universe that physicists and astronomers have come up with. It seems that the most likely scenario is something that we call the big freeze, or the heat death of the universe, where the universe continues expanding, but not fast enough that everything gets ripped apart. Instead, it will just expand forever, and galaxies will use up all of their gas to make stars. Those stars will die. Even the very low mass M stars that we now know take trillions of years to go through their life stages. So all of those stars will die. What you have left will be a bunch of white dwarfs and neutron stars and black holes. And the white dwarfs and neutron stars will radiate away their energy until they are dark chunks of rock in space. But the black holes will have their own era where they're the only things left in the universe. So if you're trying to figure out how long the universe will be around, how long will there be any energy left in the universe, you have to think about how long it takes these black holes to evaporate, because they're going to be the last
to go.
The last thing standing, yeah.
Yeah. Wow.
So those are black holes in general. I would now like to talk specifically about the black hole in our galaxy. Do you know its name?
I don't know if I do.
It is called Sagittarius A star.
Sagittarius A star. And this star has nothing to do with stars.
Correct. Correct. It's a fun little story how we got that star, the little asterisk at the end. So starting in the 1930s, astronomers noticed radio signals coming from the direction of the center of the galaxy.
Wow.
But we didn't have good radio telescopes to study them, and we didn't have infrared telescopes powerful enough to peer through all of the dust between us and the center of the galaxy. I've talked about the zone of avoidance in past episodes, and it really slowed down astronomy, the fact that we couldn't see through all of that dust and gas. So in the 1930s, we noticed this radio signal, but it took another 40 to 50 years for us to discover the specific source of that radio signal. We knew it was coming from the Sagittarius constellation direction, and we knew that there were these several big sources of radio waves, but it wasn't until 1974 when they found the specific one that was the strongest radio signal. That was discovered in 1974, published in a paper by Bruce Ballack and Robert Brown, but it wasn't named Sagittarius A star until the 80s. And it's named Sagittarius because that's the constellation it's in. A, because it's in the biggest group of radio sources in that central galactic region. And the star is because back in olden physics times, when we were first thinking about electrons and where they sit in an atom, they would use an asterisk to denote that an electron was in an excited state.
Okay.
And so they added the asterisk to the name of Sagittarius A star, one, because it was exciting, and two, because they could see that it was so strong, it was actually radiating energy into the surrounding environment.
Yeah.
Much like an excited electron, when it goes back down to its level, releases a photon. So it's releasing energy into its environment. So they saw that parallel. So it was named in the 80s, and then it wasn't confirmed as a black hole until decades later.
Wow.
The Nobel Prize in Physics was given to two scientists for their work in confirming that Sagittarius A star was in fact a black hole. Those two scientists' names are Reinhard Genzel and Andrea Ghez, who was the third woman or something to get a Nobel Prize.
I remember reading about that when it happened.
Do you remember what year it was?
Oh, gosh. Recently.
It was extremely recent.
I want to say 2021.
Close. It was 2020.
Okay.
That they won. So
no one remembers that year. So that was
a blur. Other things were happening.
Yeah.
We were busy. So it's this journey started in the 1930s, and the black hole at the center of our galaxy wasn't confirmed to be a black hole until they won the 2020 Nobel Physics Prize.
Wow, that's so recent.
I know. We are still actively learning about space.
That's almost 100 years from when we first got those radio signals.
Yeah, space study is slow.
Wow. Takes time.
So this black hole, Sagittarius A star, is about 4 million times the mass of our sun, which is not that high. I just told you about 65
compared to the
billion.
66, yeah, exactly.
Yeah. So it's 4 million solar masses. It has a diameter, because we can measure the diameter with the Schwarzschild radius or by studying the accretion disk around it. We have actually taken a picture of the black hole at the center of our galaxy, so we really can study it well now. But it has a diameter of about 15 million miles, which is bigger than the sun, but smaller than the orbit of Mercury.
Oh, wow.
And yeah, so we took this picture of Sagittarius A star with the Event Horizon Telescope, which is a worldwide interferometer. So it's several telescopes across the world working together to get a better view of this black hole. For telescopes, the bigger your diameter, the bigger your collecting area is, the better your resolution is.
Okay.
And to actually resolve or see clearly these black holes, we would need a telescope as big as the Earth. So we made one.
Wow.
Yeah. It's really beautiful. It's just amazing international collaboration. They get so much data, but some of these telescopes are in really remote locations. ALMA, which is where we recorded the last episode.
Yes.
ALMA is involved in this Event Horizon Telescope. And so some of these locations are so remote that they don't have good internet connection, so they don't send the data electronically. They physically capture the data from these telescopes on hard drives and then mail the hard drives to the scientists studying them.
Wow. I did not ever think of that.
It's wild. So they took the data in 2017. They released the picture in 2022. And the reason I sound upset about this is not because it took them a long time to analyze the data. 5 years to analyze literally like petabytes of data, that's not that long. That's fine. I'm pissed about this timeline because I submitted the final version of my book in January of 2020. And there is this line in my book where I talk about how astronomers haven't managed to take a picture of Sagittarius A star yet. And then literally 2 months later, when it was too late for me to fix things, but before the launch of the book, we got the picture. So now it just looks like the book is wrong.
I get it. Guess what? There's a mistake in my book as well.
What's yours?
There is a section that there's like one sentence that should have been formatted as if it was a title.
Okay.
But it's formatted like paragraph text.
Oh, no.
I hate that.
Yeah.
It doesn't really detract too much, but I get it. It happens.
It's true. Yeah. This is one of the issues of writing books about astronomy and actively evolving science. Like sometimes you write something and then science happens and then what you write is wrong, but it's too late to take it back.
That's how it goes. So it goes.
So it goes. But now we have the picture and we can study it and it's amazing. But that brings me to the question, how do we study black holes without actually just taking a picture of them?
Yeah.
Because it's really hard to take a picture of them. And we've only done this twice. We did it with Sagittarius A star and we did it with the black hole at the center of M87, another galaxy. There are like 3 ways, I'll say, that we can study black holes. The first is with light. We can study the light from their accretion disks and their relativistic jets if they are powerful enough for us to see them. That's one way. We can also study the gravitational effect that a black hole has on its environment. So there are stars very close to the black hole in the center of the Milky Way. And we have studied their orbits. They're stars. They're bright, so we can see them and study how they move. Actually, the way that Andrea Ghez and Reinhard Genzel confirmed that it was a black hole was by studying the orbits of stars around Sag A star. There are like 30 of them that we've been tracking for over 25 years.
Whoa.
The closest one is called S2. It's like Sagittarius 2.
Yeah.
S2 orbits Sag A star like once every 16 years. So in the study, they saw a full orbit of S2. And at its closest approach to the black hole, it's just 6 million miles away. I know that's a big number, but in space, it's really close.
Yeah.
Yeah, it's just 6 million miles away from the black hole. Do you have 6 million miles? It's like, it's so small.
Yeah, no, totally.
So small. But it gets 6 million miles away from Sagittarius A star, and at its closest approach, it moves at 7,000 kilometers per second, which is more than 2% the speed of light.
Whoa.
It's moving so fast. So when you study these orbits, you can calculate the mass of the black hole, which is what they did. And they were like, it's so massive, the only thing it could be is a black hole.
That's really fun.
And then the other way that we can study black holes is with gravitational waves. Everything makes gravitational waves. Anything that has mass makes gravitational waves, but they're usually so tiny that we can't measure them. A gravitational wave is like, it's often described as a ripple in the fabric of space-time.
Yeah.
And I don't really have another way to explain it, but I feel like that's not super helpful if you haven't spent a lot of time thinking about the fabric of space-time. But essentially, picture space as like a big blanket, and all of the stars and planets and like black holes are balls sitting on that blanket. And a heavier object will make a deeper dent in the blanket than a lighter object. And if that object moves around, it will create ripples in the blanket, kind of like a rock falling into a pond. And we can study those ripples to figure out how massive the object that created it was. But we can only do this for supermassive things. So back in 2015, I mean, people have been thinking about gravitational waves for like 100 years. Albert Einstein was thinking about gravitational waves, but it wasn't until 2015 that we saw them, or that they were published for the first time. So LIGO, which is the Laser Interferometer Gravitational Wave Observatory, sensed gravitational waves generated by two colliding black holes 1.3 billion light years away and published those results in 2015. So it's the Laser Interferometer Gravitational Wave Observatory. It's essentially two long hallways that are perpendicular to each other, like miles long, and they shine a laser down both of these hallways that meet at a right angle. And the idea is that if a gravitational wave passes through the Earth, it will also pass through LIGO. It will pass through these two hallways. And the effect it will have is like shrinking and stretching space-time. Like that's what the ripples do. It shrinks and it stretches. But by having these two hallways at a right angle to each other, when one shrinks, the other will stretch, and vice versa.
Yeah.
And like that's how you know it's a gravitational wave. And you can measure like how much they are shrinking to calculate the strength of the gravitational wave and therefore the mass of the thing that created it.
Whoa. I love that we figured that out.
Because we're essentially like it's the tiniest change in distance, but they're shining lasers down both of these hallways and measuring how much time it takes the light to get back to the source of the laser. And if it shrinks, then the light will come back faster. And if it stretches, then the light will come back later. And I love that we have been able to set up these experiments to capture signals that our ancestors could not have imagined.
Yes.
Like it's mind-boggling.
That's really... and even the 100 years ago of first getting this like wave detected. Yeah.
So that is everything that I had to say about black holes. That is not everything about black holes.
No.
There's a lot more, and there will be more episodes about stuff like this in the future. But how do you feel right now, Corinne?
I feel a lot better. I think as I said, they feel like this impending threat of, oh my gosh, here they come. They're coming for me.
But they're not.
Maybe it's because we just recently watched Moonfall, where I'm like, this is heading straight for me.
Black Hole Fall would be a much more terrifying movie.
Yeah, that would be, how would we defeat that?
We wouldn't.
I'll bet they would end up going into the center and it would again be aliens.
Right. But they did this with Interstellar, right? Like they passed the event horizon of a black hole, and no one knows what happens beyond the event horizon of a black hole. No one.
That's really wild. Yeah, I'm not as afraid as I was when we started.
Good.
Which is helped by this beautiful park that we're in. And for everybody listening, remember, tonight when you look at the sky, you are space.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.